Hi, my name is Ravi Ranjan Kumar and this is my YouTube channel I Am Physics. In this video, we are going to discuss a problem based on hydrostatic force and torque on submerged plane. So here is the problem. So let me read out the problem statement first. A liquid of density rho is filled in a cuboidal container of dimension h into 2h as shown in figure. A semicircular gate is made at the bottom of container of radius r is equal to h by 2. Let F is the force acting on the gate due to the liquid and tau is the torque acting on the gate due to the liquid about a line PQ. Then choose the correct options. So here is this diagram. This is a cuboidal container in which some liquid of density rho is filled, and this cuboidal container has a semicircular gate of radius r, and we have to find out the force exerted by the liquid inside it on this semicircular gate, and we have to also find out the torque due to that hydrostatic force about the line PQ. So in these options we have provided with some expression for force and we have to choose the right one, and some expression for the torque also. So we will be doing this problem step by step. So first we need to find out the force. So in order to find out the force, let me have a general method for the calculation of hydrostatic force on a submerged plane surface, and the formula which we will be deriving here will be applicable for a plane surface of any shape, of any orientation. Here this shape is not a regular shape, it could be any shape, and its orientation need not be vertical or horizontal, it can be inclined at some angle also. So how to find out the force on that plane surface area? So first of all we must realize that the pressure at different point on this area has to be different. The pressure profile is non-uniform because different points are at different depth from the free surface, and the pressure inside the liquid is the function of its depth from the free surface. So because the pressure profile is non-uniform, we must choose an infinitesimal area, and we can find out the force on that infinitesimal area, which will be equal to P times dA, and this P is going to depend upon the depth of that area from the free surface. So the pressure as a function of y can be written as P naught plus rho gy, where P naught is the pressure at the free surface and y is the depth of that infinitesimal area from the free surface. So once we have found out P, the force will be having magnitude P times dA, and the force in vector form can be written as dF is equal to its magnitude, that is P naught plus rho gy times dA, and its direction I have written it as n cap. N cap is a unit vector in the direction perpendicular to this surface, this direction we are having. So because this surface is a plane surface and the direction of normal at any point on this plane surface is going to be same, so this n cap is a constant vector because it is having a constant magnitude unity, and its direction is also same everywhere at every point on the surface. So finding out the net force is easy for us. For the magnitude of it, we just need to integrate the term P naught plus rho gy times dA over the whole surface, and the direction of the net force is going to be along n cap, which is perpendicular to the surface. So this integral can be separated in two parts. The first part would be P naught times dA, and the another term would be rho g times y dA. Rho and g being a constant, I have taken it out of the integration sign. Calculation, the first term is very easy because P naught is constant, that will come out of integration sign, and integral dA will be nothing but the net surface area that I have written as simply A. Now this integral y dA, if the surface is given to us, we can definitely calculate this term YdA, but we are proposing a method according to which we need not calculate that integration every time we need it, because it resembles something over which we have already worked a lot and have many different formulas already remembered for it. So how is that? So the concept of centroid of area, let me introduce for you. Centroid of area, I have given the symbol as YC, and I am defining it as integral of YdA upon integral of dA, and when we rearrange to find out integral of YdA, we can write it as YC times A. So integral of YdA resembles the calculation for center of mass of a mass distribution. Let's take a lamina of same shape as that area and mass distribution to be uniform. So how are we going to write the center of mass of that uniform lamina? So that will be according to the formula of the center of mass YCM. We can write it as integral of YDM upon integral of DM. But because it is a uniform surface distribution we have assumed, so dm can be written as sigma times dA, and sigma is surface mass density, and in the denominator also in place of dm I have written it as sigma dA, because sigma is constant. It will come out of the integration sign and will get cancelled, and we will be left up with integral of YdA upon integral of dA, which is essentially the same term as YC. So what is the conclusion here? That centroid of area YC is same as the center of mass of a uniform lamina of same shape. So once we have realized that, this integral YdA can be written as YCA, and YC will be nothing but center of mass of uniform lamina of same shape as that of area. So once we have written that, this whole term is with us, that is P naught times A plus rho g YC times A, and when we take A common, we will be left up with this term P naught plus rho g YC, which is nothing but the pressure at the centroid of area. So the steps to find out the net force, net hydrostatic force on a plane submerged surface, what we have to do, we have to first locate the centroid of the area, and centroid of the area will be nothing but the center of mass of a uniform lamina of same shape. So once we have found out PC, all I need to find out is the area of that surface, and when we multiply these two terms, the net force will be known to us, and its direction obviously will be perpendicular to the surface. And the beauty of this formula is it is not only applicable for some some regular shapes, but some irregular shape also, as long as we know how to calculate the centroid of that area. And it is also not dependent on the it is not also only applicable for some specific orientation, but it is also applicable for any orientation of that plane surface in a submerged state. So that same thing we will be using for the above problem, because this time we have a semicircular gate, and it's this line is at depth h from the free surface. So in order to find out the force, the first step would be to locate the centroid of this area, and centroid of the area will be coinciding with a uniform lamina of the same shape, and we understand the center of mass will be at 4r by 3 pi from O. So its distance from the free surface, which I have termed as YC, that will be equal to h minus 4r by 3 pi. So we will be using the formula which we have derived earlier. So first we need to write the pressure at the centroid, which will be nothing but P naught plus rho g YC. YC is nothing but h minus 4r by 3 pi, and the area of this semicircular shape will be half of the circle, that will be equal to pi r square by 2, and when we will be using the formula which we have derived, F is equal to Pc times A, and when we substitute these values we will be getting P naught plus rho g h minus 4r by 3 pi whole into pi r square by 2, and simplifying we will get this expression over here. Here in this expression we have a P naught term, but in the question, when we look at the options, here we don't have, for any of the expression of force, P naught term is absent. So that means that in this problem, the atmospheric pressure has been neglected. So if we also neglect the atmospheric pressure, P naught, but we will be left up with only this term over here. So ignoring atmospheric pressure, P naught will be equal to F P naught, ignoring the atmospheric pressure, F will be equal to rho g h cube by 2 into pi by 4 minus 1 by 6, which we must notice is actually the option B. Now for the calculation of torque, we will also try to have a general method which will be applicable for any plane surface, but this time the formula which we are uh, going to derive, or the method for which it will be applicable, is for lamina which will be vertically oriented. So here we go. So here for the semicircular shape, in order to find out the net torque about a given axis, first we need to find out the force, and due to that force we need to find out the infinitesimal torque, and we need to integrate in order to get the net torque. So the method is clear. Let's take an infinitesimal area dA, and on that dA the force that would be acting due to the liquid will be coming out of the plane, and its magnitude will be dF, and dF will be given as P times dA, which we have already seen as is equal to P naught plus rho g y times dA, and the torque due to it will be the arm of that force into that force itself. So arm clearly, because we need to find out the torque about this diametric axis. So the distance of this point of application of this dF will be, from the axis will be h minus y. Y is the depth of that element from the free surface. So that will simply be equal to h minus y into P naught plus rho gy into dA. And in order to find out the net torque, we need to have its vector addition, but realizing that the torque due to force on any infinitesimal area will be perpendicular to that surface only. So the torque will be directed only towards this axis. So in order to find out the magnitude, all I need to do is integrate this term over the whole area. So when we do this integration and separate a few terms, we will be getting this P naught into h integral of dA plus rho g h minus P naught integral of y dA minus rho g and integral of y squared dA. The first two term, how to calculate, we have already seen. Let's see. P naught into h, and the integral of dA would be nothing but simply the area of this, that would be pi r square by 2. For the second term, rho g h minus P naught, and the integral of y dA we already know how to calculate. That is centroid of area times the area. Centroid of area will be h minus 4r by 3 pi into the area, that is pi r square by 2. In order to calculate the third term, that is rho g into y square dA, let's try to resemble it with something which we already know. This integral y square dA, we know it as second moment of area, and its symbol, let's say, is IA. I am defining this IA as integral of y square dA, and this kind of integration also we have earlier done, where when we were finding out the moment of inertia of a lamina. Like for example, if a plane surface or planar lamina we have, how do I find out the moment of inertia of it about a particular axis? Let's say that will be I will be equal to integral of y squared dm, where y would be the distance from a line or axis. So here y is taken from the free surface or the water line, that is y squared dm. And if it is a uniform lamina, then we can say that dm will be nothing but sigma times dA. So we have to find out this integral y square sigma times dA, and sigma will come out of this integration sign because it is uniform, and we will be left up with sigma into y square dA integral. But sigma is surface mass density, so it will be equal to m by a times y square dA integral. And now when we rearrange, because we are interested in this term y square dA integral, which is nothing but the second moment of area, that can be rearranged to write it as IA by m. So second moment of area, that is IA, is equal to IA by m, I being the moment of inertia of planar lamina. And now, like, what does this tell? What does this expression tells us about? So I have divided this moment of inertia term with mass of the body and multiplied with the area of the body. So what will it do? Like, for example, if the moment of inertia is I, that is kmr square. So if I divide it by m, so this m term will be eliminated, and multiply it with a, then in place of m, this a term will come. So all we have to do in order to find out the second moment of area is, in the formula for the moment of inertia, we replace its mass with its surface area. So moment of the second moment of area will be equal to k times a times r square kind of thing. Like, for example, this geometry of uniform lamina, what we need to do in order to find out the second moment of area, we need to first calculate the moment of inertia of this thing about the water line, this line, what a line on the free surface of the water. So let's first try to find out the moment of inertia, and that is easy. Everybody has already done it, but let me anyway have it. So like, we need to find out the moment of inertia of this semicircular lamina of uniform mass distribution about this water line. So first of all, we anyway know that about this axis, the moment of inertia will be mr square by 4. And according to the parallel axis theorem, this moment of inertia about this axis can also be written as moment of inertia about a parallel axis passing through center of mass, this axis, plus m times distance between these two parallel axes, which is 4r by 3 pi. So rearranging, we get the moment of inertia of this lamina about an axis passing through the center of mass, that would be mr square by 4 minus m times 4r by 3 pi whole square. So now we must use parallel axis theorem one more time in order to find out the moment of inertia of this shape about the water line, and that will be I will be equal to ICM plus m times the distance between these two parallel axes, which is nothing but h minus 4r by 3 pi, and the square of it. And when we substitute the value of ICM from here, this is the expression which we get. So this is the moment of inertia. How do we get the second moment of area? Replace this m by the area of the shape, which will be nothing but pi r square by 2. So let's do the same thing over here in order to calculate the third term, rho g y square dA integral. This y square dA term is second moment of area, which will be equal to all we need to replace is m with area itself, and this pi r square by 2, and this term we have already calculated. So this whole expression gives the torque due to the hydrostatic force about an axis passing through this line here, and taking P naught is equal to 0 as suggested by the problem and as suggested by the options given, and for R is equal to h by 2, this will be the torque which we will get, that would be rho g s to the power 4 by 4 into 1 by 3 minus pi by 32. So that's it. Thank you very much.